Hello everyone. In this video, I'll explain all about orthogonality. Orthogonality of two lines, orthogonality of two curves, and orthogonality of two surfaces. When we say these lines or curves or surfaces are orthogonal, what are the conditions? We will see both geometrically and algebraically. See the first concept, that is orthogonality of two lines. See, when I draw two straight lines, these two straight lines are perpendicular if the angle between them is 90 degrees. That is, geometrically, by looking at the given two straight lines, I can say whether those two lines are perpendicular to each other or not. We know that every straight line can be represented using the equation ax plus by plus c equal to 0. That is the algebraic representation of the given straight line. So the first straight line, if I name it as a1x plus b1y plus c1 equal to 0, and the second straight line as a2x plus b2y plus c2 equal to 0, the two lines are orthogonal if the product of their slopes equal to minus 1, m1, m2 equal to minus 1. So m1 is product of the m1 is slope of the first line. So slope of the first line is given by minus a by b. A by b means coefficient of x divided by coefficient of y. So that is minus a1 by b1. m2 is minus a2 by b2, coefficient of x by coefficient of y. So if you substitute that condition here, you will get a1 a2 plus b1 b2 equal to 0. So this is the condition for orthogonality of two lines algebraically, because every time you can't draw the graphs of the lines and you can't check are they orthogonal or not. So the geometry studied with the help of algebra is analytical geometry, where each line is having its own name. With the help of those equations, we are finding are they perpendicular or not. See, for example, two lines are given here. I have to check are they perpendicular. When I draw the graph of these two lines, now I can see these two lines are perpendicular to each other. But algebraically, you have to check a1 a2 plus b1 b2, is it equal to 0. So let us write what is a1, coefficient of x, which is 2, b1 is coefficient of y, which is 1. a2 is coefficient of x in the second equation, b2 is coefficient of y in the second equation, which is minus 2. Let us substitute those values here. 2 into 1 plus b1 is 1 into minus 2, that is equal to 2 minus 2, that is equal to 0. Therefore, this condition is satisfied. Hence, the lines are perpendicular to each other. This is how we check the orthogonality in the case of lines in 2D. Here the lines are given in 2 dimensions. Now let us see how to check the orthogonality of lines in 3 dimensions. Any line in 3 dimensions is represented using vector equation or using this Cartesian equation. If a line is represented using vector equation, then it is given as r vector equal to a1 vector plus lambda into b1 vector, r vector equal to a2 vector plus mu into b2 vector, where b1 and b2, these two vectors give the directions of the given two lines. Now these two lines are orthogonal if the angle between those two vectors b1 and b2 is 90 degree, means their dot product is 0. That's b1 vector dot b2 vector. If you get it as 0, then those two vectors are perpendicular, but those two vectors will give you the directions of the lines, hence lines must be perpendicular. This is when the lines are given in vector equation. So if the Cartesian equation is given like this, x minus x1 by a1 equal to y minus y1 by b1 equal to z minus z1 by c1, and this is the second equation of the line. These two lines are perpendicular or orthogonal if a1 a2 plus b1 b2 plus c1 c2 equal to 0. If you substitute the same in this, you are going to get this condition. because B1 is A1 I cap, B1 j cap plus C1 k cap, like that. So the condition for orthogonality in 3D for the two lines is A1 A2 plus B1 B2 plus C1 C2 equal to 0, where A1 B1 C1 are direction ratios of first line, A2 B2 C2 are direction ratios of second line. Let us take one example. See, this is the example. Here two lines are given. Geometrically, when I draw these two lines in 3D, so I will get these two lines. This is the first line and this is the second line in black, lines in black. Now see here, geometrically I can say that these two lines are perpendicular because angle between them is 90 degree. Now algebraically, to prove it, you need A1, B1, C1. These are the direction ratios of first line, A2, B2, C2. Let us check A1, A2 plus B1, B2 plus C1, C2. So 7 into 1, 7, minus 5 into 2, that is minus 10, then 1 into 3 plus 3. So 7 plus 3 is 10 minus 10, that is equal to 0. So we got the required condition, hence we can conclude that the two lines are perpendicular to each other. Now the same lines can be represented in using the vector equation, that is R vector is equal to A vector plus lambda into B vector. The direction of this first vector is given by, that is B vector equal to B1 vector 7 cap minus 5j cap plus k cap, B2 vector equal to I cap plus 2j cap plus 3k cap. Now, if you find out the dot product is between these two vectors, that is same as this condition, then you will get it as 0. Therefore, the lines are perpendicular to each other. This is how we check the orthogonality of two lines in 3D. Now about orthogonality of curves. Two curves are orthogonal if the angle between their tangents at the point of intersection is 90 degree. If this is satisfied, then we say that those two curves are orthogonal. See, for example, I have taken these two curves y square equal to 2x and y square plus 2x square equal to 1. One is an ellipse and another is a parabola. Now, at the point of intersection, these two are the points of intersection. You have to draw tangents. So, one tangent for the parabola like this. Okay, another is tangent for this ellipse. Now, look at this. These two tangents are perpendicular to each other. These are perpendicular to each other. And in the second case also, here also, if you draw the tangent like this, those tangents are perpendicular to each other. Hence, these two curves are orthogonal. That is, geometrically we can see here. But when you have two curves, algebraically if you want to prove these two curves are orthogonal, what you have to do is, you have to get the two tangents and those two tangents are perpendicular. So, two lines are perpendicular if the product of their slopes m1 into m2 equal to minus 1. So, you need to get the slope of the tangent to the first curve, then slope of the tangent of the second curve. So, how to get the slope of the tangent? Here we use the concept of derivative. So, derivative geometrically it is nothing but it is a tangent to the given curve. It is the slope of the tangent to the given curve. So, if I want the slope of tangent of first curve, then I need to find out m1. Okay, for that you need dy by dx, because dy by dx gives you the slope of the tangent to this curve. So, you have to differentiate. So, differentiate the first equation, you will get 2y dash equal to 2 into derivative of x is 1. So, 2 cancels, y dash equal to 1, y dash is equal to 1 by y. This is your m1, slope of the tangent to the first curve. Next, similarly differentiate the second, 2y dash plus 2 into derivative of x square is 2x equal to derivative of 1 is 0. So, y dash plus 2x is equal to 0, which gives you y dash is equal to minus 2x by y. Okay. This is m2. Now those two curves are perpendicular, m1 m2, which is equal to minus 1. If you get this, then we say that those tangents are perpendicular, hence the curves are also perpendicular. So 1 by y into minus 2x by y, this is the product m1 into m2, which is equal to, so simplify this, equal to minus 2x divided by y square. Okay, now we didn't get minus 1, we have to substitute y square as 2x. So minus 2x divided by 2x, that gives you minus 1. Therefore, when you get m1 into m2 equal to minus 1, means the tangents are perpendicular to each other, hence the curves are also perpendicular to each other. The given two curves are orthogonal. This is how we check the orthogonality of two curves by finding their slopes using the concept of derivatives. Now, these curves are orthogonal because the angle between the tangents at every point of intersection is 90 degree. Here also you can check, there are 2 points of intersection of these two curves. At this point as well as at this point of intersection, angle between tangents is 90 degree. Therefore, these two curves are orthogonal. In case if only at particular point of intersection angle is 90 degree, then they will specify, prove that these two curves are orthogonal at this particular point. Now these two curves are orthogonal because at every point of intersection the angle between the tangents is equal to 90 degree. Now about orthogonality of surfaces. Here two surfaces intersect orthogonally. Two surfaces are given by f of x comma y comma z equal to 0 and g of x comma y comma z equal to 0. These two surfaces intersect orthogonally at a point, at a given point, if fx gx plus fy gy plus fz gz equal to 0. This condition is obtained from the gradient of the functions. So gradient vector is a vector which is normal to the given surface. So what we are doing is del f means finding the gradient to the first surface, and then del g means finding the gradient to the second surface. The gradient is always a normal vector which is normal to the surface, means perpendicular to the surface. So therefore, if you want the angle between two surfaces, you have to find the angle between their normals. If the angle between their normals is equal to 90 degree, then we say that the two surfaces are orthogonal at that particular point. So suppose if these two surfaces, these are the given two surfaces, they intersect at a point, and at that point you have to draw normal to first surface, then draw normal to second surface. If suppose here, somewhere over here, if these two normals are perpendicular to each other, then we say that the surfaces are perpendicular at that particular point. Therefore, to find normal, so we need to find out del f, gradient of f, that is nothing but dou f by dou x into I cap plus dou f by dou y into j cap plus dou f by dou y into k, dou z into k cap. This is using the vector calculus. This is the gradient to the first surface. Gradient means it is a vector which is normal to the first surface. So you can name it as n1 vector. n2 vector is nothing but gradient of the second surface. That is dou g by dou x into I cap, same thing, plus dou f g by dou y into j cap plus dou g by dou y in z into k cap. So now if you want to, these are the normals to those surfaces respectively. Now if you want to find out whether these two surfaces are orthogonal at this point, then you have to find out angle between these two surfaces, that is n1 vector dot n2 vector. If their dot product is 0, then the two surfaces are orthogonal. So dot product is 0 means what? Fx into gx, same condition, plus fy into gy plus fz into gz equal to 0 means the two surfaces intersect orthogonally at that particular point. So this is the way of showing it algebraically. Geometrically, we have to draw normals to those two surfaces at the point of intersection, and we have to measure the angle between those two normals. That's the same thing, because now drawing the normal and checking the angle between those two normals is not easy when you have surfaces. In between two lines, checking the angle between those two lines is easy. You can directly say by looking at the graph of those two lines, are they perpendicular or not. But now it is not that easy. So algebra plays an important role. How to do this algebraically? See, the first surface f equal to f of x comma y comma z equal to, all terms should be on one side. So you can write 7x square minus 12x minus 5y square minus z. This is the first surface. Next, you have to get the second surface, g of x comma y comma z equal to x y z square minus 2. You have to find out fx, fy, fz, then gx, gy, gz. So now here fx means first partial derivative of f with respect to x. So in the case of two-dimensional curves, we were finding there dy by dx. But in the case of three-dimensional curves, here we need partial derivatives instead of derivatives, because when the concept of partial derivatives comes, when there are more than one independent variables. Here there are two independent variables x and y, one dependent variable z. Therefore, we need to go with the concept of partial derivatives. So we are finding the components of derivatives. So fx means partially differentiating this with respect to x. So 7 into derivative x square is 2x, that is 14x minus 12. Then derivative of y square 0, derivative of z is 0 with respect to x. Now with respect to y, this derivative 0, 0 minus 10y, then 0. Fz with respect to z, derivative is minus 1. Rest all terms 0. Gx, this is x. So it is yz square constant, derivative of x is 1, derivative of 2 is 0. Then with respect to y, xz square constant, derivative of y is 1. With respect to z, xy constant, derivative of z square is 2z. Now we need at the point 2 comma 1 comma minus 1. We need to find out all these values at the point 2, 1, minus 1. Put x equal to 2, y equal to 1, z equal to minus 1. So when you put x equal to 2 here, 28 minus 12, that is equal to 16. Then here y equal to 1 minus 10, then z equal to, anyway it is constant here, minus 1. Here in this case same, 2, 1 minus 1, y is 1, z is minus 1, so it is 1, x z square, so that is also equal to 2 into minus 1 whole square, 2, then x y 2z. So 2 into 2, 2 2s are 4, then with a minus 4. Now you need the condition, that is fx gx plus fy gy plus fz gz, which is equal to, you have to get it 0 if they are orthogonal. So fx here, 16 ones are 16, minus 10 into 2 minus 20, minus 1 into minus 4 plus 4. So this gives you 20 minus 20, that is equal to 0. We got the value 0. Therefore, these two surfaces are orthogonal at 2, 1, minus 1. There are other points of intersection also. Here it is asked at that point, at this point of intersection, these two surfaces are orthogonal. That we have to prove. At some other point of intersection, the two surfaces may not be orthogonal. Their angle between their normals may not be equal to 90 degrees. So it depends. So we don't here say that the two surfaces are orthogonal. We say that two surfaces are orthogonal at that particular point if this condition satisfies at that particular point. If at every point of intersection the angle between their normals is equal to 90 degrees, then the two surfaces are called as orthogonal surfaces. So this is all about orthogonality. We have seen the orthogonality between lines in 2D as well as in 3D, then orthogonality between curves, and finally the orthogonality of surfaces. I hope you understood the concept. Thank you for watching.